Yeah, good. So I'm going to do two things. So the talk has two intertwined components. One component, as you see in the subtitle, is a case study. This has already been published, so if you're interested in the details, I invite you to look at the paper about realism about Newtonian gravity. But when you look at that paper, you will find nothing about entity realism, and not even about causal realism. Because the framework within which that case study is set is actually the framework of effective realism. I will tell you a little bit about what that is. And the obvious question then arises how effective realism relates to entity realism. And this is the other component of my talk. This hasn't been investigated yet, not even by myself. I've only started thinking about the connection for this workshop, and it's very much work in progress. So I'm just going to give you my first ideas on how the two might connect, and possibly resulting in something that deserves the name effective entity realism. So let me first tell you why the case of Newtonian gravity is interesting. If you know the scientific realism debate a bit, you may be sometimes a bit puzzled, at least I am, about the status of Newtonian mechanics in that debate. It is kind of curious if you think of it. So, I mean, it clearly is a highly successful theory, and it's a theory we no longer believe to be true, because there was Einstein and general relativity, and we also think of quantum mechanics that in some parts replaced Newtonian physics. So it should be an obvious example of a theory that spells trouble for realism, just like phlogiston and caloric. But if you look at those famous lists of such theories that were once believed to be true based on their success, but now are no longer believed to be true, often you don't find Newtonian physics. For example, in Lauden's list, it's not there. And even in more recent lists, like Peter Vicker's list, it's not one of those examples. And why is that? So part of the reason is probably that many people, and including many physicists, want to say that Newtonian physics is approximately true. So it wouldn't qualify as a counterexample to the no miracles argument. But it's seldom, or one could even say never made clear what kind of approximate truth that is. Because, I mean, it's obvious that on the empirical level, yes, we have approximately true predictions by Newtonian physics. And also on the formal mathematical level, we can define approximation relations. But what about the ontological level? In what sense is Newtonian physics approximately true? So this is never made clear, and one way to read my talk is also an attempt to give some kind of answer to that question. Well, one could ask whether entity realism can help in that respect, and at first sight it cannot, because. Now, if we think of some central concepts of Newtonian physics, like gravitational forces, or you could also think of gravitational fields, gravitational potentials, these would be entities about which we may want to be realists. And now, given that Newtonian theory was abandoned, one may hope that one could be realist about those entities, even if the theory was abandoned. But I don't think this would really work, because, I mean, the theory and entity are really so much connected in that case that it's, I think, hopeless to try and separate them, as you could, for example, I mean, in Hacking's famous example of the electron. It's much clearer how one could experimentally interact with electrons without having a precise theory about it, or even having many people experimenting on an electron having different theories. I don't think that such a story can be told in the case of Newtonian forces. Just a brief side remark for those who are interested in more metaphysical matters about forces. I mean, I know that one can have all kinds of discussions about the precise metaphysics of Newtonian physics, whether forces are really the entities that are what's real according to Newton, or whether it's fields or potentials. I'm not talking about that distinction here. For me, for the sake of this talk, I would say forces and fields and potentials, they go hand in hand ontologically. What I'm asking is a more fundamental question, namely whether any kind of Newtonian ontology is tenable or not. And then we can still ask whether it's forces or anything else. So that's the question I'm addressing. Yeah, so since this straightforward sense of entity realism that we have in the case of electrons doesn't work here, problems for realism about Newton's theory directly affect realism about gravitational forces. So at least at that level of description, entity realism doesn't seem to help much. What I want to show in my talk is still that there is some part or some component of entity realism, namely this, what one could call an experimental attitude, that can strengthen realism about Newtonian gravity by joining it to that framework of effective realism, which I'm now going to introduce. So one source of inspiration for my ideas here is quite an old paper by Jessica Wilson. She treats Newtonian mechanics as kind of special science. Like, I mean, the term special science is kind of strange. It usually refers to all sciences except fundamental physics. And yeah, in that sense, Newtonian mechanics is a special science because we found that it's not describing the fundamental nature of space-time. So it's a higher level theory, so to speak. There are other ways of articulating that, and one particularly interesting way is by taking this notion of an effective theory. It was originally, it comes from quantum field theory, and there is this paper by Williams who applies it to the scientific realism debate and argues for realism about quantum field theory as an effective theory. And that's where the notion of effective realism comes from. And I then thought that this doesn't only have to apply to quantum field theory. Why not apply it to other non-fundamental theories, such as non-relativistic quantum mechanics? That's what I did in that paper from 21, called Quantum Ontology Without Speculation. And of course, I have to kind of broaden the notion of effective theory, because in quantum field theory, there is some quite precise mathematical specification of what counts as an effective theory. I have a more, maybe naive or common sense notion of effective theory, if one wants to call it that. Just that a theory is effective if its domain of successful application can be specified by requiring some physical parameters to be in a certain range. So the idea is that mostly it's energy. If the energy is in a certain range, not too high, then the theory saves all the phenomena in that domain. And it's understood that if you go to higher energies, theory will break down, but that doesn't affect its effectiveness on that level. Now, if we're talking about Newtonian gravity, we can specify some parameters that need to be in a certain range for the theory to work. So velocities shouldn't be too high, they should be small compared to the speed of light. And we shouldn't be too close to massive objects. That's what this equation says. So here we have the so-called Schwarzschild radius of an object with a certain mass. And as long as you're not too close to such objects, Newtonian physics works very well. So in that paper on non-relativistic quantum mechanics, I already made some remarks on Newtonian gravity, but not very elaborated. And then Juha has written a paper in response criticizing effective realism. And he put the focus on Newtonian physics. And we're going to see his arguments against effective realism in that domain. And he's arguing that Newtonian physics is really a problematic case for this kind of realism. And then there were partial responses to Saatchi's criticism. One paper by Robertson and Wilson called Theoretical Relicts, and a paper by Ladyman and Lorenzetti called Effective Ontic Structural Realism. And here you see also where I got the idea to come up with effective entity realism, because I'm thinking, oh, if the structural realists can do it, I can do it as well. I can kind of claim effective realism for our side, and you're going to see how this is supposed to work. And then specifically about the case about Newtonian gravity, I thought the responses by these people were not quite satisfying, so I gave what I take to be a more complete response in a paper that just came out about this case of Newtonian gravity. So, what is the criticism that Saatchi voiced? So, effective realism is a realism about the ontology of effective theories, and you could also call this effective ontology, so non-fundamental ontology, in other words. And Saatchi says that a blunt appeal to effective ontology results in theoretical tensions that both philosophers and scientists have been keen to relieve, often by carefully articulating or explaining away tension-inducing ontological commitments in order to achieve overall theoretical coherency. So the problem is that if you have these higher level theories and they have their own ontology, then it can happen that this ontology is in contradiction to the ontology of the fundamental theory. And what needs to be done then, according to Saatchi, is some kind of articulation how this can be, and some achievement of overall theoretical coherency. And in some cases, this will involve explaining away ontological commitments, so you're no longer ontologically committed to the upper level theory. And he gives some examples of when such theoretical tensions arise. And the examples actually might suggest that he's a general eliminativist about higher level ontology. So one example he gives is light rays in classical optics, which he says, of course, with wave optics, we then found out that light rays don't really exist. And also in the case of gravitational forces, he would argue the same thing. But it's not an overall eliminativism about higher level ontology that he's arguing for. So he's very explicit about that. So he says, I'm not suggesting that scientific realists should be only committed to fundamental ontology. So, for example, he endorses realism about viruses. And of course, we know that viruses are not fundamental objects, but they are fine, according to Saatchi. Whereas in other cases, the higher level ontology, such as gravitational forces, is not fine. The question then, of course, is what is the difference? So how do viruses differ from gravitational forces ontologically? These theoretical tensions that Saatchi spoke about, they probably don't arise if two theories have just very different subject matters. And that seems to be the case in the virus case. So we have virology and we have fundamental physics. It's clearly that they speak of different things, so no theoretical tension. In the case of Newtonian physics, that seems to be different, because it seems that Newtonian physics and general relativity make conflicting claims about some common subject matter, namely gravity. And then we have a problem. We have these theoretical tensions. Now, the response given by these people that I mentioned earlier, like Robertson-Wilson and Lehmann-Lorenzetti, is to claim that actually, even here, we have, in some sense, different subject matters. So what Robertson-Wilson argue for is a thing called vertical reduction. So it's clear that there is a reduction relation between Newtonian physics and general relativity, but it's what they call vertical, which means that the two theories can ontologically coexist. So the higher level theory abstracts away from the more detailed lower level theory. It provides successful descriptions of a different higher level subject matter. So it's a different subject matter of the higher level theory as of the lower level theory. And they go on to argue that in that case, we don't need to eliminate the higher level ontology, because it's just, as in the case of viruses, I mean, virology is also at some point supposed to be reducible to fundamental physics, but still we think viruses exist because it's a different subject matter than what fundamental physics speaks about. In slightly different terms, but I think the same general idea is voiced by Lehmann and Lorenzetti. So they speak of different scales. Newtonian gravity and general relativity describe reality at different scales, and they have different ontological implications at each scale. In this sense, the ontology of each theory does not rival the ontology of the other, and including both kinds of gravitation in our general ontology does not entail any inconsistency. Yeah, okay, if that works, then fine. But it's not entirely clear that it really works. So let's look a little bit closer at why Sartzi thinks that there is a problem. So the relation between Newtonian physics and general relativity. And here Sartzi again speaks of the difference between the virus case and the case of gravitational forces. So he says the key distinction between viruses and atoms, molecules, and apples and other non-fundamental entities on the one hand, and Newtonian gravitational forces on the other, is that only the latter are flatly contradictory with the more fundamental theory in question. The Newtonian concept of gravitational force is inconsistent with the general theory of relativity. The Newtonian concept is one that causes acceleration in an inertial frame of reference. In general theory of relativity, however, gravity comes out as conceptually equivalent to fictitious inertial forces in Newtonian mechanics that only appear as a function of the system being described in an accelerating non-inertial frame of reference. So the distinction is between what's called non-inertial forces. These are the forces that cause acceleration in an inertial frame, and these inertial forces that only arise in accelerating frames of reference. And there is indeed a sense in which you can interpret gravitational forces even in general relativity. So they don't they're still there in some sense, but they are interpreted as inertial forces. You can think of Einstein's elevator thought experiment. So, I mean, when we are in an elevator that is at rest, of course, we feel that gravity is pulling us down. But this force, according to general relativity, is nothing else than the force you experience in an accelerated frame of reference. Because in the thought of general relativity, an elevator at rest with respect to the Earth's surface is, in fact, an accelerated reference frame, because it's not in free fall. So that's the way of thinking about it in general relativistic terms. So gravity as an inertial force, and Sartzi points out that this is flatly contradictory to how gravity is conceived of in Newtonian terms as a real non-inertial force. Now, how can we avoid the contradiction? Because as we saw, like people like Leiden and Lorenzetti, they think there is no contradiction. So the beginning is that mathematically we can decompose the space-time metric of general relativity, which is usually denoted by this tensor G mu nu, and decompose it into two components. One is this eta mu nu, which describes a flat space-time. So as we have in special relativity, where no gravity is taken into account, plus some deviation from flatness, gamma mu nu. Now, if this deviation is sufficiently small, you can perform some kind of approximation procedure, and it turns out that this approximates a term that can be interpreted as proportional to a Newtonian gravitational potential. And so in the approximation, this actually gives rise to some kind of Newtonian gravitational forces, which are non-inertial, because it's Newtonian physics that comes out of this approximation procedure. Now the question is, how much ontology should we read into this interpretation? Okay, well, mathematically it's possible, of course, but is it is it ontologically serious? And here I found that intuitions differ. So, I mean, I tend to be skeptical of this kind of mathematical move, or I mean, not as mathematics, but if you put too much ontology into it, because I mean, in this case, there are some well-known examples where you may run into troubles. So whether this gamma mu nu, the deviation from a flat spacetime, is sufficiently small, this depends on the context. So think of the famous example of the perihelion precession of the planet Mercury. This is one of the key successes of general relativity as opposed to Newtonian mechanics. You can only detect the deviation between the two theories if you really look at the planet Mercury for a long time, for several years. If you look at Mercury for a short time, it behaves just like any other object around us. We can perfectly describe it in Newtonian terms. So it seems that whether this gravitational force that pulls Mercury towards the Sun is non-inertial or inertial depends on how long you look at it, which seems kind of strange. Maybe it is not that strange. I mean, Leiden and Lorenzetti, they don't explicitly argue in this way, but that's the best sense I can make of their argument of their claim that there is no contradiction. So what they need to say is that, yeah, okay, there is this kind of scale dependence. It's a time scale dependence, why not? But it accords very well with the key principle of ontic structural realism, namely the scale relativity of ontology. So yes, ontology is different at different scales, and that's not a problem. On a large time scale, there is this kind of inertial force of gravity. On a smaller time scale, there is a non-inertial force of gravity. So if you have that intuition, you're kind of close to structural realism. I would call this intuition structuralist. And for those who don't share it, I have another term, namely experimentalist. The idea is that even experimentalists, or you can also think of entity realists in that context, they also tend to accept a kind of ontological scale relativity, but only in a more restricted sense. So one example that would work well here is the proton, which at one energy scale, so if you're not applying too much energy to it, it clearly is indivisible. You cannot divide a proton if you don't have enough energy. So that seems kind of a physical basis for claiming that the proton really is indivisible at that energy scale, whereas it becomes divisible at a higher energy scale. If you apply more energy, then there is a physical change of the situation, and then it's true to say that the proton is divisible, and it's no longer true to say that the proton is indivisible. So There is a scale relativity of ontology in that case, but the experimentalist would claim that the two cases are different, whereas the structuralist would say no, they're both unproblematic. So this response that Ladyman, Lorenzetti, and in some other terms also Robertson and Wilson have given to Sathi's challenge is not convincing if you have like experimentalist intuitions. We need a stronger argument if we want to be realist about Newtonian gravity. And before I go on with the case, I just want to make the connection to entity realism a bit more explicit. So we've heard already about causal realism here in this workshop. It's one way to develop entity realism, and I think it already also goes somewhat beyond manipulation, because it's not a hacking-like manipulability approach, but more oriented towards Cartwright's idea of causal explanations. So we've also heard what the basic idea is, namely that there is this kind of specifically strong warrant, which is called causal warrant, that depends on three criteria: empirical adequacy, material inference, and non-redundancy. And so in this case, I think empirical adequacy is unproblematic. It is to some extent built into the very notion of an effective theory. So the effective theory is supposed to save all the phenomena in a clearly specified domain. So that's more or less what empirical adequacy says. But then the criterion of material inference is, I think, problematic for this derivation of non-inertial gravitational forces that we saw above. So with this mathematical decomposition and then approximation procedure, this has a very formal flavor, I would say, because it depends on the complete theoretical framework. And that's also where it can kind of pin down the difference to the proton case, because in the proton case, it's much more hands-on and a clear physical notion of why the two energy levels differ. And there, I think one can speak of a kind of material inference to the proton's indivisibility at a certain energy scale. So this kind of derivation of non-inertial gravitational forces doesn't work for the experimental realist. We could still say that gravitational forces are there, but they're just inertial forces. But this is kind of problematic with respect to the non-redundancy criterion, because usually the inertial forces are regarded as redundant, because they can always be eliminated by a choice of reference frame. So they only appear in Newtonian physics, they only appear in accelerated reference frames. In general relativity, it's a bit different, but still you can always find reference frames in which they don't appear. So they seem somewhat redundant. Now to reply to that, we have to look a bit closer at the notion of inertial forces and what role it plays in Sathi's argument. So Sathi actually doesn't only speak of an inconsistency between the two pictures, the Newtonian and the general relativistic one, but he also says, it's not just that it's inconsistent, but if we find out that the gravitational forces are inertial forces, and then we add the premise that inertial forces are not real, he speaks of fictitious forces, then we can conclude that the gravitational forces are not real. And the discussion so far has centered on premise one, and we found that there is not really causal warrant against premise one. Maybe there's some theoretical warrant according to this derivation, but that's not really satisfying. So, but let's look at premise two. And that's where the case study comes in. And I'll be very brief about this. So there's this experiment, GRACE, Gravity Recovery and Climate Experiment, where they have two satellites orbiting the Earth. And then the idea is to detect mass anomalies on the Earth's surface or even in the atmosphere, because they lead to differences in gravitational potential. And this then influences the relative velocity of the two satellites. So by very precisely measuring those differences in velocity, you can draw inferences about how the mass is distributed on Earth. So mathematically, it looks like this. You have this density of mass within the volume of the Earth. And this then creates differences in the gravitational potential. And the idea is to, I mean, this you can somehow measure by measuring these differences in velocity of the two satellites, and then you draw inferences about the mass distribution on Earth, which is here in this integral. So this works because we have Newtonian physics and it's linear, and we can regard the gravitational potential as a superposition of all these contributions from these infinitesimal mass elements. All very well. And it wouldn't work if we were to describe the situation in a purely general relativistic framework without any Newtonian or post-Newtonian approximation. Because there we only have Einstein's field equation, which are nonlinear, and we just couldn't write down such an equation and couldn't perform these calculations that they do for the mass distribution. Now, one might think that it is just due to our limitations. If we had sufficient computing power, it might work. But I think there's a good claim to be made that this is not just about us. So a pure general relativistic treatment would require so much computing power that no physically possible device could execute it. Of course, I cannot prove this, but in the paper, I have some arguments why this is probably so. And if this is right, then this gravitational potential, the Newtonian one, is indispensable in a maximally non-anthropocentric sense. So it's not just about our limitations, but it's about the physical limitations on computation. And that makes it what Ladyman and Ross, in their famous book from 2007, called a real pattern. So here we have the connection to the ontic structural realism literature, and I'm coming to the conclusion now. So Ladyman and Lorenzetti also draw the connection to real patterns, and as part of what they call effective ontic structural realism. But as we've seen before, their approach relies on this kind of structuralist intuition that we can give ontological sense to this mathematical derivation of non-inertial Newtonian forces. And this is just, as I said, theoretical warrant. But now that we have this experiment and this argument from physical computability, it seems to me that we have causal warrant. We might call it experimental warrant because it's quite closely connected to modeling, and so I think I'm not really opposed to your idea there. So the three conditions for causal warrant, I think, are fulfilled. The Newtonian potential accounts for the observed relative movements of the satellites, and we have concrete values that are inferred from the measurements of the movements. So that's a material inference. And if what I said before is right, it is indispensable for the task of calculating mass distributions. So there's non-redundancy. So that's where it comes together. So we have a kind of effective entity realism. We can talk about labels. I'm not sure if maybe effective experimental realism would be better, and effective causal realism would make the connection to my earlier causal realism more explicit. So I'm not yet sure how to call it. But I mean, the important message is that I think the two can go together, effective realism and some kind of entity realism. And it tells us something, namely that we can be realist about the gravitational force potential and the associated forces without claiming that these forces are non-inertial, because that was a problematic claim based on this theoretical warrant, which created, according to Salzi, the incoherence. And this, I would say, gives precise ontological sense to the claim that Newtonian's gravitational theory is approximately true. So it gave us some true knowledge about what's out there, namely that there are these forces, but it also made some false claims, namely that they are non-inertial. And this is actually of interest for any scientific realist, not just for entity realists or effective realists, but because Newtonian physics is an important case. So it gives us some more precise account of the sense in which Newton's theory is approximately true. So that's it. Thanks.